Hi, I'm Ilya, and today I will talk about vision language action models, or simply VLAs. That is one of the most promising approaches to train robotics policies nowadays. If you've seen different video on YouTube where robots doing real life tasks like doing laundry or like folding some clothes or doing dishes or cleaning the bedroom or kitchen or something like that, most of these robots are powered by VLAs. Also, VLAs is the topic that people were asking about in the comments for my previous videos, so I'm glad that I finally made it, and I think it should be interesting for everybody to discuss this topic. While preparing for this video, I realized that there are a lot of interesting content to cover, and if I try to squeeze it inside one video, it will be too much. So I decided to experiment and try a new format where I starting a series of videos. This first video today will talk about the high-level idea of VLAs, how typical design or architecture of VLA look like, and what is basically relation of between VLAs and LLMs, and where do we currently stand in terms of the VLA performance and usage patterns. In the upcoming following videos that I will try to post every few weeks, I will talk about some particular models. I will cover Pi0 from physical intelligence. I will cover Gr00t from NVIDIA and SmolVLA from HuggingFace LeRobot. I will talk much more about these models, about their architecture, about the ideas that they use for training, and go through the corresponding papers. And also, I will talk about how to fine-tune these models on your own data sets and how to make them work on home with some cheap hardware like this LeKiwi robot that I have right here. In my previous videos, I shown how to train a simple single-task policy on the particular robot in the particular environment to autonomously complete this task. So you can watch my videos about SO-ARM or about LeKiwi. I talk about it in details. But if we try to discuss what we want to see in the ideal policy, then probably we want one policy to be able to control different robots, to be able to do multiple tasks, to be able to do what we tell this model in the plain language, to be able to extrapolate and adjust to new environments, new tasks, new robots, and so on and so forth. And the best analogy that we have right now is probably like ChatGPT and other top LLMs, where you can ask any question, and this kind of service can answer your question, maybe sometimes with hallucinations, sometimes with some mistake, but more or less can give you some answer. And this is where we want to be eventually with robotics policies 2. And the interesting thing that VLAs, of course, don't solve this yet, but it's definitely a very big step towards this future, towards this solution. And also there are much more connections between LLMs and VLAs, because VLAs are technically just little bit adjusted LLMs in terms of the actual models behind them. So yeah, let's talk about it, and let's look into VLAs and see how they work. As I said before, VLAs are kind of LLMs for robots. So let's first of all look at the naming and see what every word and every letter in VLA means. First of all, let's start from LLMs. So LLMs, or large language models, are some models that can accept text as input and then predict the next token that is also text. The evolution of LLMs led to VLMs. So if we remove this large, that is very subjective and actually change its meaning, what's considered large, what is not over time. So if we remove the word large but add word vision, we will get vision language model, or VLM. So this is again is some evolutionary step of LLMs. And these models accept text and images as input and predict the next text token. And sometimes, optionally, they also can predict image tokens and generate new images, but quite often it's made as a separate model that is just connected to the VLM. If you look at all the biggest LLMs out there, like Gemini, ChatGPT, Claude, and so on. All of them are already VLMs, so you can send the pictures to them. You can even send much more modalities and different files, and they can work with this inputs. And the same is true for open source models. So there are a lot of models that are trained on both text and images and can process both of modalities. And finally, if you want our model to control the robot, it should be able to predict actions for the robot. So let's move the last word model away from the abbreviation and add action as the last one, and we'll get Vision Language Action Model, or VLA. And this is the model that accepts text, images, and the state of the robot as input, and then predicts robot actions. You can see that names of these types of models are very, very similar, and they're very related. But in practice, if you look at how these models works, it's modern names. It's basically the same model. So the core of all of these models, VLA, VLM, and the LLMs are the same transformers. It's basically the same LLMs inside. So let's look a little bit deeper into it, and let's discuss how the model works on the architectural level. First of all, let's look at LLMs. So LLMs in their core have transformer. It's some type of machine architecture. And basically most of the LLM is just many layers of transformer decoder stuck together. Of course, there are a lot of other parts. There are like some other logical steps and so on, but simply speaking, it's like very big transformer. And this transformer can receive text tokens embeddings as input, and then after processing them through many layers, first of all, it encodes all of them into some new contextual representation. And finally, the last prediction of the model is used to predict the next token, or like you can simply think about it as the next word in the text. And it's repeated after regressively. So you predict like next token, then you use this next token as the last input, and you predict the next token and next token and next token, and so on and so forth. So this is how transformers work, and how LLMs work overall. So it's get some text as input and then predict the next text token. Now, if we simply add visual backbone to this model, we will get VLM. So visual backbone, historically, I think it's usually was some CNN, convolutional neural network. Nowadays, it's mostly other transformer-based encoders. But basically, this is some model that takes image as an input and outputs one or multiple vectors that encode the information in this image. So usually all these parts of the model are pre-trained on the big scale data sets. So for example, LLMs are pre-trained on basically a lot of text that covers most of the internet, and visual backbones are pre-trained on the huge amount of different images, and they try to use them for different tasks. And then if you take these two pre-trained models, pre-trained LLM, pre-trained visual backbone, and then simply attach outputs of the visual backbone to the inputs of LLMs, and then also train this model a little bit more on some extra tasks that include both images processing and text generation, you will get VLM. So again, VLM kind of takes two pre-trained model. Both of them are pre-trained on the internet scale datasets. Then touch them together, and the result is VLM. After some extra fine-tuning, extra training, it starts to uh, effectively kind of deal with both images and text simultaneously. And then finally, we need to move to VLA. And to do it, we need to add an action head, some part of the model that will predict actions. And there are different ways to do it. One way, it's probably a bit simpler, is to predict action tokens inside the same LLM. So what we do, we just extend our LLM a little bit and say that now the tokens that it predicts are not only text token, but they can be action tokens. One of the ways to do it is just to take the existing dictionary of all the tokens, take the least popular tokens in this dictionary and replace them with actions. So just tell the model, okay, these tokens don't mean text anymore. They mean some robot actions. And at the same time, you get this action tokens from the actual robot data. So you somehow either cluster this data or somehow compress this data as in fast to transform the original continuous actions into discrete tokens. And yeah, and then you just do some extra training of the model using the robotics dataset collected from the real robots. And eventually, your model starts to predict these tokens right from the same, basically, LLM backbone. But this is not the only way to do it. Another way that is very popular and it's used in many different VLA models right now is to add this extra action head. Sometimes it's called action expert, for example, in Pi0. The idea of this action head is that it's usually separate model or some extra, at least, weights for the same LLM. So it's kind of separated part of the model that takes the information encoded inside LLM as some input that it can refer to. But inside it, it uses what's called diffusion transformer. So transformer is kind of the same architecture that I discussed before, and diffusion is kind of the way how to train this architecture to predict something useful. And in case of diffusion, what we do, we train the model to gradually remove noise from the noise. So gradually transform noise into some realistically looking useful actions of the robot. And all this process of transforming noise into actions is conditioned by what is generated inside the LLM. So this diffusion thing, this action head, looks at what LLM predicted, because LLM supposed to have done all the main thinking, and then uses like specific technology to move from the noise to the actual continuous actions that will apply to the robot. And this is more or less how all VLAs look like. Of course, there are a lot of differences, and we will talk about these differences in the upcoming videos when I go deeper into each model. But strictly speaking, this is it, more or less. So all the VLAs that you can look at, they have very, very similar architecture. They can use different LLMs, they can use different visual backbones. There is like different way how to add state. For example, in this picture, I added state to the LLM. Sometimes it processed separately completely. Sometimes it's added to the action head. Sometimes you predict action tokens, sometimes you use diffusion or flow matching, that is also type of diffusion. Sometimes you do both of them simultaneously, sometimes you add some extra tasks for training and so on and so forth. So there are a lot of moving parts, a lot of ideas how you can improve these models, but most of the models in their core nowadays look like this. And the idea and the main idea behind it is that, as I already mentioned, LLMs are pre-trained on the ton of text data. So they already have a lot of knowledge about the world kind of incorporated into LLM. Visual backbone is also trained on the huge amount of images. And it learns how to extract some very important patterns or important information from these images. So when you combine everything together and start to train this model for robotics applications, it already has a lot of kind of knowledge that encoded into the weights of the models. And this is why it allows you to do like more tasks, to generalize to new environments. It allows you to give some text commands to the robot, and so on and so forth. So this is how it works. And again, in my following videos, I will discuss much more details on how exactly it is implemented in different models. Actually, there are like some other models that are not technically VLAs because they're not based on LLMs, but they're doing like very, very similar things. They also have some text encoder and vision encoder. And I would say formally they're not called usually VLAs, but they're very, very similar. So I think most of the things that we're discussing right now will be applicable to these models. But yeah, let's not go into these details for now. Attention, LLMs, transformers, diffusion, flow matching, all these things, they are very popular right now and they're used across different areas. So robotics is one example, but actually most of them came from Gen AI, they came from like NLP and image generation. So if you don't know about these things, I highly recommend you to read about it, to like watch more videos, because it's like really important. It's like very useful, and I wouldn't be surprised if there will be like more and more areas where these types of models and these approaches show good results. Regarding robotics, so I have like one video about multimodality in robotics, and this video is not exactly about diffusion and flow matching, but it touches these topics and it explains how exactly diffusion and flow matching work in robotics use case. So you can watch it to understand it better. I think it's also a bit related to VLAs. And I will talk more about transformers and attention logic in the following video, when we will go deeper into the each of the VLA models that I want to cover. There are many important aspects that tell you how good the policy is. It's like success rate on different tasks, what type of task it can complete, what is the duration of this task, what is the dexterity, what is the multimodality level that present in this task, and so on and so forth. And of course, all of these are gradually improving when you get like newer policies and so on. But I want to talk about a different thing about how these VLAs actually change the policy usage pattern, how they bring this concept of fine tuning to robotics, and what is the analogy in the NLP area where similar changes happened in the last, let's say, 10 years or so. So yeah, this is very subjective. This is just my thoughts. It's not based on like any paper or so. So I'm just like sharing a little bit of my view here. So be very skeptical to what I'm saying here. And the first pattern is actually no end-to-end policies. So this is where the whole industry was, let's say 5-10 years ago. And actually it's still very useful and widespread. And if you look at the industrial robots, or like robots in warehouses or some other cases, they usually not using any end-to-end policies. They use like more classic robotic approach, and basically most of the robots that are actually generating money right now, they don't use these fancy policies yet. So this approach is again very classic. It's usually means that you separately develop perception, planning, and control part of your policy, and then combine them into one pipeline. This pipeline usually has a lot of manual corrections, a lot of deterministic, non-trainable logic, and so on and so forth. If you look at open source, then there is, for example, this ROS2 ecosystem that has a lot of different algorithms, a lot of these kind of pieces that you can combine into one big robotics project. And if you look at the analogy in NLP, then it also will be like classic NLP before neural networks. When you basically, to solve any text-related problem, you need to do a lot of pre-processing, like stemming, lemmatization, spell checking, and fixing. Then you use some things like TF-IDF to create features from this text, and then you train some simple model on top of it to solve your particular problem. So you needed to develop like a whole pre-processing, training, prediction pipeline to solve any single problem. And often these pipelines were different for even different problems. And then this neural networks mostly brought this idea of training end-to-end policies. So in NLP, it usually were LSTM or some other types of RNNs. So you still needed some data set, you still needed to annotate it, so to get some labels for each piece of text. But then you simply train the model end-to-end, and this model could solve this one, like your particular task. The same thing came to robotics with policies like ACT or diffusion. And so you can collect your data set, you can annotate this data set. So basically, it's usually combined in the case of robotics. And then you simply train one policy end to end to solve this particular task using this particular robot in this particular environment that you use for data set collection. And this is type of the problems that I cover in my other videos about SO-ARM and about LeKiwi. Also, you can be kind of flexible here, and you can also experiment with your own models. For example, I developed this dot policy like this. So the idea is simple. Again, you collect data set, and then you train some model end to end to solve the particular problem from this data set. The next pattern that is actually introduced by VLAs, that is the topic of today's video, is fine-tuning. So I think mostly VLAs in robotics are fine-tuned right now. And the idea of this fine-tuning is that you take a big model, relatively big, train it on some big mix of different data sets, probably with different problems inside. And during this training, you expect your model to learn a lot of important patterns that can be useful in other problems as well. And then when you need to solve this particular problem, you just fine tune, or in other words, just train a little bit more your pre-trained model on this particular data set. So in case of robotics, you just take the same data set that you used on this step 2, but instead of training policy from scratch, you train policy initialized by some pre-training. And yeah, the idea that you supposed to kind of generalize much more and train much faster using this approach. In NLP, it was a very big step, and I think there were like some models like Elmo, Yolemfit, Bird, and so on that did it. Especially, I think Bird was very kind of loud because when they released, they beat a lot of benchmark, and they really improved the quality of many text models on many like text data sets a lot. I'm not sure if I can say it for robotics because we don't have many very good benchmarks that are very reliable, because in robotics a lot of things depend on the data set, on the robot, on the environment, and so on and so forth. So there are no like really good widely accepted benchmarks there. But yeah, I do believe that this idea, or at least like this concept of fine-tuning, will actually help a lot to improve the quantitative features of the policies and improve the results for different robots across different tasks. And of course, you can already do it at home. So all these models, like Pi0, Gr00t, and SmolVLA, they are open source. They are available for fine-tuning. And this is exactly what I will be talking about in the next few videos. The next pattern, I called it fine-tune for the robot. And it's different from fine-tuning on the task, because here I assume that you have pre-trained model. Again, you have some data set, probably much bigger than in the fine-tuning for the task. And your data set collects a lot of different tasks, a lot of different problems there. And you still do fine-tuning, but you don't do fine-tuning to train your policy to complete the task. You do fine-tuning to train your policy to control the robot. And you expect that this policy will be able to complete much more tasks than your fine-tuning data set has. So I think this is, again, it's very similar to the previous step, but here we expect much more extrapolation, much more generalization from the model. So you should be able, again, to fine-tune it for new robot. and it should kind of preserve all the knowledge about completing similar tasks from the training data set based on other robots. I don't think it's available openly yet. If you look at the demo videos from frontier labs like physical intelligence or DeepMind, then we can see that things like Gemini Robotics or Pi-05, they're doing something very similar. So they really generalize a lot for like new environments, new problems, new tasks, new robots, and so on. But again, these are still just demo, and they're not so available for like in open source or so on. So yeah, I think this is again where all this frontier research is happening, but seems like it's not there yet. Also, companies like LeRobot from HuggingFace, they're doing very cool things by training VLAs on the publicly available data sets using SO-ARM, for example. And maybe it will also help to solve this problem. So if you have a lot of data from very, very similar robots, then probably this policy will generalize well when you fine-tune this policy on your instance of the same robot. So I think maybe in SmolVLA V3, V4, or V5, we will see a lot of cool generalization. And then finally, we get to this plug and play pattern. So what I mean by this, imagine that you have a policy, and then you connect your robot completely new for this policy. So this policy never seen this robot before. And out of the box, it can control it. So it can solve the problem that you ask it to solve using completely new robot without any training or fine-tuning. I call it almost plug and play because there should be some calibration like step or maybe very, very small fine-tuning just to like let policy know how to control the robot and what all the actions for this robot mean. So I don't know, maybe there should be some 10 minutes process that somehow teach your policy how to control the robot, and that's it. And there are no like hours of training or fine-tuning required to control a new robot. As far as I know, this stuff doesn't exist. So I think that even in frontier labs, they do a lot of training on like huge data sets collected on their own robots. So I don't think it's done yet. Maybe the closest thing how you can think about it is something similar to the experiment that I did with MCP for robot control. So I basically let all these state-of-the-art LLMs like GPT, Gemini, and Claude control my robot, zero shot, without any training. And it even could make some progress, and it could complete some very simple pick and place tasks, but it was very, very slow, and I think success rate was pretty low. So I couldn't say that it actually works. It's fun as an experiment, and if you imagine that all of this stuff that I did there, and I explained in my video, if you imagine that it works much better for much more complex tasks with higher speed and higher success rate, then this will be what I call plug and play. And yeah, of course, it doesn't exist yet, but we've seen that it happened in NLP. So the analogy will be ChatGPT and other services that appeared after, like Gemini, Claude, Grok, and so on. So I think 10 years ago, nobody believed that it would be possible to do the stuff that ChatGPT is doing right now. It's literally like zero shot, can solve a lot of problems. Yes, it can make mistakes. Yes, it can hallucinate. Yes, there are still a lot of problems, but again, it was very revolutionary when it was developed, and it's like very, very cool, and really like pushed this NLP area forward a lot. And I hope we will see something very, very similar in robotics, especially if this VLA will like reach the same scale as this frontier LLMs have right now. And again, it's like very, very subjective. It's just my very high level thoughts and feelings about where the whole area stands right now. I'm not sure if all of this is actually correct, and I'm not sure that it will happen the same way it happened in NLP. But this is my very high-level vision that I just wanted to share here. Okay, so we discussed the main idea of VLAs. I will go deeper into the logic of the particular VLAs in the future videos, but right now, in the end of this video, let's talk about preparation for it. So some things that it's better to do in advance. So when you fine-tune your VLA policy, you need to collect data set that you will use for fine-tuning. Usually you collect it using TIL operation. And I talk a lot about it in my previous videos about SO-ARM and LeKiwi. So please watch them and try to follow them. I also recommend you to first learn how to train the single task, simple models, and only then go to VLAs, because the processes are very, very similar anyway, but it's much easier to start from the simple models and then kind of go for like more and more complex use cases. In my case, I will fine-tune all the models on a very simple task, very similar to what I did in the previous videos, where I trained my robot to pick the ball and put it inside the cup. And I already collected data set for it. So people also often ask some questions about data set, whether it should be clean, whether it should be whether it should contain any mistakes, and so on and so forth. So I sharing my data set that I collected. You can find it on my HuggingFace page. And you can see the quality of this data set. So most probably it will not be really useful for you to just train on this particular data set. It will not give much value as is, but you can just look at the quality of this data set, and you can see that it's pretty noisy. So it's not very clean. So I have some mistakes there. I have a couple of episodes where I actually failed the task because I dropped the ball, like I dropped the cup. I have some episodes where I have some recovery, where like I cannot grab it from the first time or something like that. So recovery is usually good. These like fails are usually not so good. But again, if you're talking about this simple task, then this kind of quality of data set that you can see right now is more than enough. If you want to go beyond it, if you want a model that generalize across different tasks, across like different environments, and doing everything with very, very high success rate, then probably, yeah, you need much more data, you need much better data, and so on and so forth. But again, for some simple experiments at home, this amount of data, like here, like 55 episodes in total, around 15 minutes, should be more than enough for you to experiment with. And now a quick trailer for the future videos. So I actually already fine-tuned all three VLA models on my data set. And I would say it was pretty straightforward. So generally speaking, you just follow the instructions that are provided by the creators of these models, and like 95% everything works. And then there are like 5% where you need to do a little bit of troubleshooting, but it's pretty straightforward usually. So yeah, you can see on the screen right now how my robot completing this task. So yeah, it can work. Again, it's not ideal. Maybe I didn't really compare it with other approaches. I'm not sure if the success rate is even higher than for single task policies, but yeah, at least it works. And for this initial intro, this is what I wanted to achieve. So yeah, stay tuned, and like in the next few videos, I will go model by model and explain how these models work and how exactly you fine-tune these models to complete what you want. That's it for today. I hope you enjoyed this video and learned something new. Also, as it's ongoing series, I encourage you to leave comments with any questions. So if you have any questions, something wasn't clear in this video, or you want me to cover some topics, or maybe you want me to talk about some other models or some other things related to VLA, then just go ahead and ask these questions, leave a comment about it. I think if I have enough comments, I will actually adjust the content of the future videos or just add some Q&A part in the end of each video. So yeah, let's see how it goes. So yeah, please ask your questions or leave any comments you want below this video. Also, please like, subscribe, click this bell button, and yeah, I will tell you more and show you more examples in my next videos. So see you soon. Bye.